Hello, I'm Byeonghyeon Lee, and I'm going to present our paper titled Sharp-NeRF Grid-Based Fast Deblurring Neural Radiance Fields Using Sharpness Prior. Before diving into our work, I would like to start with the background of this paper. Neural radiance fields have demonstrated the impressive performance in rendering 3D objects and scenes. However, it suffers from visual quality degradation when the input images have been captured under imperfect conditions like defocus blur. Lots of the previous approaches have attempted to model the scene blurriness to reconstruct a clean image from the blurred images, but they require long training time. Thus, the goal of this paper is to build fast deblurring neural radiance fields. To do so, we propose to use learnable discrete corner, sharpness prior, and patch sampling. Most of the previous works adopted MLP-based blur corners. They use an additional MLP to produce the blur corners, so it inevitably requires additional computation for MLP forwarding. Also, those MLP-based corners are limited in their expressivity as small MLPs use it, so it is not well aligned with the grid-based neural fields. Another line of research is using grid-based blur corners. It has an advantage that it can quickly produce blur corners with simple indexing. However, to the best of our knowledge, those grid-based corners are only applicable to address the camera motion blur. Also, they are fixed, not learnable. This slide illustrates the overview of Sharp-NeRF. Among lots of parts, our main contributions are patch sampling, sharpness prior, and discrete learnable corner. First, we adopted random patch sampling instead of random ray sampling. Defocus blur occurs due to the interruption of the neighboring pixels, which happens due to the shallow depth of field of the camera. In order to model such interference of the neighboring pixels, peripheral region of the interesting pixel must be rendered as well. As the figure shows, the patch sampling can provide duplicate neighboring rays so that it can efficiently reduce the number of the volumetric rendering. In this case, the ray sampling requires 36 rays to render 4 pixels, while patch sampling takes only 16 rays to render the 4 pixels. Such difference even becomes bigger if the number of the required neighboring pixels is large, which is inevitable to model the partially defocused region. We also use sharpness prior to model the scene blurriness. We use sharpness measure operator to compute the sharpness of each pixel. There are various sharpness measure operator from traditional SML and Tenengraph to neural net-based operator. In this work, we use neural net-based one, DME-net, to estimate the defocus map which represent the sharpness of each pixel. We estimate the focus map of every training view and quantize it uniformly into NK values. The quantized defocus map is used as a sharpness level map which divides pixels into NK groups based on their degree of sharpness. This sharpness level map is a sharpness prior which is further used when initializing the blur corners. And this sharpness prior is computed only once as a part of the pre-process and takes less than a couple of minutes. As it is computed before training, it does not affect the subsequent training and testing times. Lastly, we adopt multiple trainable grid-based blur corners. Every training view has its own blur corners, and each sharpness group in each training view shares one blur corner. Instead of optimizing per pixel blur corners, we train NK blur corners, which is identical to the number of the unique sharpness level, and pixels in a same group share a blur corner for effective optimization. Using per pixel sharpness level map, we can easily get per pixel blur corners through simple indexing. It is worth to note that applying appropriate blur corners to appropriate regions of the images plays key role to estimate the scene blurriness, because different regions in various depths of fields have various degrees of blurriness. The rest steps for training are: first, we feed the ray patches to the backbone grid basin neural fields and get the sharp image. Then we crop the sharp image into several small image patches. The width and height of the image patches are identical to those of the blurred corners. Then the cropped image patches are weighted summed with the per pixel blur corners to get the blurry images. Lastly, we compute the L2 loss between the rendered blurry images and training images. For the inference stage, the process is simplified to just rendering the sharp and clean images using grid-based neural fields. This is because we assume that neural fields will render the sharp image and we apply convolution to that sharp image to make it blurry. So just feeding rays to the backbone neural fields are the only step for rendering sharp image, and any other steps are not required. Thus, the required inference time is identical to the backbone grid-based neural fields. To validate the effectiveness of our method, we conducted experiments on real difficult dataset and synthetic difficult dataset. We evaluate our method with several evaluation metrics, including the full reference metrics like PSNR and SSIM, and also no reference metrics like Nike and Brisk. As the difficult blur is inevitably produced when we take the picture with long depths in real world, the provided reference images also contain some difficult blur. So we evaluate the reconstruction quality with no reference metrics, which evaluate the image quality without any ground truth or reference image. As indicated in the graphs, the Sharp-NeRF achieves the comparable results to other MLP-based models consistently under various image quality evaluation metrics. It even attains state-of-the-art performance under Nike metric while reducing training time to less than a half hour, which is the shortest training time among all Deblurring neural radiance fields model. These images illustrate the qualitative results of our method. We can see that Sharp-NeRF can reconstruct the sharp and fine details from the blurry images. To summarize, we propose fast Deblurring neural radiance fields. Our approach introduced the patch sampling, sharpness prior, and discrete learnable corners. We proved the effectiveness of the proposed method under various evaluation metrics. Our method achieves the state-of-the-art performance under no reference metric and the training time. This concludes my presentation of the paper. For more detailed information, please refer to our paper. If you have any further questions, please feel free to reach out. Thank you.